We'll finish chapter 29 with some ideas on manipulating power series. The function 1 over 1 minus x has a power series representation that looks like this, which converges on the interval from -1 to 1, the open interval from -1 to 1. We just did the e to the x not long ago in a different lesson. And its power series looks like this, and it converges for all values of x. Now, even though they have different intervals of convergence, there is some overlap between the two, and we can combine the two together. For example, if we add the two functions, we get the power series that looks like this. Now, we can manipulate that series simply by doing some algebra on the inner portion of the summation and come up with a power series that looks like this. Now, typically, when we deal with the summation notation for power series, we want to make sure that our power series involves some stuff with an x to the n at the end of it. So that basically is what we need all of our power series to look like. Not that this one is not correct, it's just not in the right format. Now here's a power series for e to the x. One of the things that we oftentimes need to do is to multiply this power series by some term involving x. So for this one, if we multiply e to the x times x squared, that just means multiply the power series for e to the x times x squared. Now in the power series, you notice that the index is the variable n, and we're multiplying by some x's. Well, unless these have n's in them, this can be carried back and forth across the integral sign, the summation sign. And so we could write this as the sum of 1 over n factorial x to the n with the x squared on the inside of the summation. And then, of course, we can do some algebra on the inside as far as simplifying or manipulating that expression. Now, we're going to take the function 1 over 1 minus x and its series representation and do a substitution. So here, we're going to be substituting a 2x in place of the x. Well, the series representation for 1 over 1 minus 2x will be the same as the series representation for 1 over 1 minus x, but with the x replaced with a 2x. And so there's our new series. Now, we can actually determine the interval of convergence here just by doing a little substitution. Here's another substitution using the same function. You can see we're going to be replacing the x with a negative x squared to get the power series for 1 over 1 plus x squared. And likewise, we can determine this interval simply by the substitution. Now, using the power series for 1 over 1 minus x, we're going to expand it out and show you that when we do the derivative of the power series, we could simply do the derivative of each term individually. The derivative of the 1, the derivative of the x, the derivative of the x squared, derivative of x cubed, derivative of x fourth, and so on. Now that comes out to be the generic version, nx to the n minus 1. So basically what we're saying is when you do the derivative on a power series, you just use the power rule on the thing inside the summation. Now also notice the first term of this series was a 0, which corresponds to n equals 0. Well, you could do without that 0 and still have the same series, so the index on the derivative could begin with a 1. And let me show you on that same series what would happen if we integrated each term individually. The integral of 1 would just be an x. The integral of x would be an x squared over 2. The integral of x squared would be x cubed over 3, and so on. And again, the power rule on x to the n would be x to the n plus 1 divided by n plus 1. And so the integral, again, on the sum of x to the n means we simply use the power rule on the inner portion of the summation. And this is summarized with the two formulas where, again, this is any center. So this could be x minus some number, x plus some number, and all this is showing you is this is what the power rule looks like. Now we'll use this little hint to at least help us out in coming up with our intervals of convergence. Notice that we're saying that the radius of convergence for derivatives and integrals are the same as the radius of the function, not the interval. So if we take this power series, here's what a few of the terms would look like to help you get a handle on what we're doing. We can determine by the ratio test the interval of convergence for this. And of course, here's what the ratio test looks like. We plug in the n plus 1, we divide by the original function, simplify, and do the limit. Well, we've done this before. The limit of n over n plus 1 is 1, and we just get the absolute value of x. To be convergent, that has to be less than 1. And so we know that the radius of convergence for this function is a 1. Now we didn't test the endpoints yet, so we don't know the interval of convergence, but we know the radius of convergence is a 1. That means when we do the derivative of this in just a moment, we know its radius will be a 1. When we do the integral of this in just a moment, we know its radius will be a 1. Now let's go ahead and determine the interval of convergence for this. So if we test x equals 1, we get the harmonic series, which we know diverges. X equals negative 1, the alternating series, which hopefully we remember converges. So here is the interval of convergence for f of x. Again, the radius is 1. It's just that this one does indeed converge for negative 1, but not for 1. Now, by the power rule, the derivative of that is an n times x to the n minus 1 over n, which would come out to be just x to the n minus 1. Now, to determine its interval of convergence, when we use x equals 1, we get diverge. When we use x equals negative 1, it also diverges. So even though it has the same radius of convergence as the original function, its interval is slightly different because it does not converge at negative 1 as the original function did. Likewise, the integral by the power rule would be x to the n plus 1 divided by n plus 1, leaving the n alone, which means if we checked x equals 1, we see this converges. If we check x equals -1, we see it converges. So the interval of convergence for the integral does include both the -1 and the 1. Now the last topic we want to investigate is that of changing the indices. So if we had a power series, for example, that started at n equals 2, and for some reason we wanted that to start at n equals 0, then it's kind of like a substitution. We're going to use an I to be an n minus 2, and then plug in place of the n's an I plus 2. Notice that comes out to be, in the bottom, I plus 2 equals 2, or I equals 0. So that gets us the 0 that we wanted at the bottom. And notice what happens here. The n is now 2 larger, and this n is now 2 larger. So again, that observation is simply saying that if you look at this, if you decrease the index by 2, you have to increase that variable on the inside of the summation, and vice versa. Now to streamline that, here's what we will do. If we want this n equals 1 to be an n equals 0, that means we need to reduce that by 1. So we need to be decreasing by 1 here. That means that on the inside of the summation, every n needs to be increased by 1. So there's the new summation. Now, very similarly, we may need to manipulate the exponents. For example, this n minus 2 may need to be changed to just an n. And to do that, we need to increase the n by 2 on the inside of the summation, which means we would need to decrease the n by 2 on the index.